Hi everyone, welcome to the channel. Today we'll be looking at this problem called connecting cities with minimum cost. And the difficulty for this problem is understanding the theory. And so first we could take a look at the problem. We have n cities number from 1 to n, and we're given connections, which has connections I, and you have city 1, city 2, and the cost. And then you want to represent the cost, well, the connection is both ways, so we have an undirected graph, and then the cost tells us how much the edge is worth that connects node 1 and 2, for instance. And for this problem, essentially it's asking us to we want to find the minimum cost for every pair of cities. So there needs to be a path that connects all the cities together, and if it's impossible, then we return -1. And so this framework where every pair of cities is connected is the minimum spanning tree. And so for starters, understanding what a minimum spanning tree will help. And essentially a minimum spanning tree is exactly that every pair of cities will have a path connecting each other. And the way the minimum spanning tree is found is by organizing the edges by increasing cost. And then after doing so, choosing the smallest edge first and only adding the edge if there is no cycle that is created. And the algorithm that does that is Kruskal's, and that's the algorithm I just described. So for this problem, it's important to understand what is minimum spanning tree. After understanding minimum spanning tree, then it's about understanding what's Kruskal's algorithm, and that is the algorithm to find the minimum spanning tree. And then the third part is how do you detect an edge? And the way that I'll detect an edge is with union find. And so that's another component to understand. If you would like me to make a video on union find or Kruskal's, please let me know in the comments below. Otherwise, I'll be proceeding with these concepts. And also, I have a website. The link is in the description below. And I also have my GitHub where all the source code will be posted. And the website will serve the purpose of giving additional resources, such as I'm going through an actual interview or doing a practice problem, what is going through my mind and what kind of mistakes I make. The reason why I post this is hopefully it will help you improve in your journey of learning data structures and algorithms. And on the website, I also have videos on technologies, and source code to that will also be in the GitHub. And all these things are in the description below. And without further ado, let's begin with this problem. So we said that the cost needs to sorted, the edges need to be sorted from the smallest to greatest, and we know that the edges are represented by cost and they come from connections. So the first thing is we need to sort that. We'll do dot sort, and then when you set key equals lambda, you're able to decide, basically because we want to sort by the second element in each of the connections. And so this x will represent one of these lists, and then x of 2 will give us the cost. Now once we have them sorted, we can have an parents array for union find. And in this array, the ith element represents the ith node. So that's why we know that we need n+1 nodes. And then the value in that ith index represents the parent in the connected component. And so connected component is something else that for this problem one needs to understand, but I can explain it briefly, which is an example is these 3 nodes. They are a connected component because there's a path between each of them. And so we see here 1 and 2 is in a connected component, and then 3 and 4 is in a separate connected component. So this is useful unifying for edge detecting edges, because if I say connect 1 and 2, well, let's take this example. If I say connect 1 and 2, now the parent for 2 becomes 1. Well, I could choose the parent to be 1 or 2, but let's say the algorithm chooses the first node seen as the parent. And so if I chose that, then 1 is the parent of 2, and 1 is the parent of itself in this connected component, because I chose this edge. And then let's say I choose 3. After I choose 3, if I wanted to use this edge, then I look to see the parent of 2, and it is 1, which is different from the parent of 3, which is itself. So then these two can be connected. But now 3's parent is also 1, 2's parent is also 1, and 1's parent is 1. So this is the connected component with these 3 nodes. Then if I choose this edge, I see that the 2 nodes involved, I'll check their parents. 3's parent is 1, and 1's parent is also 1. So because the parents are the same, I know that this edge will create a cycle. And because of Kruskal's, we're choosing from increasing edges. So at first I would choose this edge. Then these would become connected component. Then I choose these two, and then the parents would be 3. And so afterwards, if I chose this edge, I would see that 1's parent is 3, and 3's parent is also 3. So then I'm known edges created, and I would not add that edge to the minimum spanning tree. So that's just an example of how the union find will work with the parents array. And initially, all the nodes are parents to themselves, because parents of themselves, because there are no edges chosen. So there's no way, no connections have been made. So we'll initialize that. And then the n plus 1, because we have n nodes, and each of them will have its own self as parent. Then the next thing is to implement the find definition, a find function. And the find function is something that's key in union find. The purpose is to look for its parent. And the way the parent is found is by, well, let's say we want to find the parent. Let's say 2 and 1 connect, and then the parent of 2 is 1, or the parent of 3 is 1, and 3 is connected to 2. So the first thing is we look for the parent of 3, which is 2, and then the parent of 2, which is 1. So essentially, we keep on searching, and let's say all 3 of these are a connected component. What we do is we keep on searching for the parent until the ith index matches the parent, because the way the union find is created and designed, the parent of a connected component will have itself as the parent. And so if we do that, we initialize and we have a node that we're searching for, and so we look for the parent, and we say the parent is parent's node, since we're looking in the parents array. And then while the node is not equal to parent, because if it is equal, then we found the leader of the connected component. Then we set node equal to parent, because we need to search for the next parent. So we need to go higher in the level, and then the parent will also need to look for the next level. So after we change the node, we make the parent the new current node. We need to find the parent of that current node. And so that's why this is a parents of node. And then in the end, once we find the leader of the connected component, we return that node. Now the other thing is, for the Kruskal's algorithm, is that the number of edges chosen for a minimum spanning tree is the total number of vertices minus 1. And so we'll need to keep track of the number of edges that we use. An example is, we see these 3 nodes. We see the minimum spanning tree is 2 edges. Now this example, it's not possible to connect these because there are not enough edges, and we'll also need to take that into account. But this can be taken into account because the theory is that we need exactly total number of vertices minus 1. And so we see here we're only given 2 edges, we have 4 nodes, total number of vertices is 4, minus 1 is 3, but we only have 2 edges, so in this case we would return -1. And we'll include this shortly. So we also need to keep track of the cost because the whole purpose is to return the minimum cost. And like I said before, we need the edge count. Now we iterate through each of the connections, and we take each element. So we have node 1, then we have node 2, and then we have the current cost. Now we have to check if there is a cycle. Well, first thing to check is, yeah, we do need to check if there's a cycle, and we know there's a cycle if the 2 nodes that we're adding, they have the same parent, because it means they're already connected. So that's why we do find node 1 not equal find node 2. So now we know that there's no cycle that's created, and then we can add the edge. And the way we add the edge is we update the parent of the second node to the parent of the first node. So we look inside parents, and we do find node 2. So now we have the parent of node 2, and we set that equal to the parent of node 1. So we're connecting node 2's parent to node 1's parent. And then for the cost, we increment the cost because we're using an edge, and then the edge count is increased by 1. And then if the edge count equals n plus 1, this goes into the vertices, or the theory from minimum spanning tree, which is that we need v minus 1 number of edges. So when we get to n plus 1, we will exceed that, and so we will return the edge. And the last thing is to take into account example 2, where we don't have enough edges, or it's possible that we finish so if we don't have enough edges, then we return -1 if edge count less than n minus 1. Also, we return the cost. All right, let's just look through code, make sure everything looks good. Find node, parents node. Okay. All right, looks good to me. Let's just run and see if it works. Okay, that looks good. Yeah, it's pretty nice on LeetCode. You're able to copy and paste this. But yeah, when solving this problem in an interview, it's good to come up with these examples yourself, and I'll include that in my website so you guys can see what kind of examples I came up with to solve this problem. And all right, looks pretty decent. All right, let's submit. Awesome. Okay, so it's not the fastest code. We could look into how to improve that. But space, it's pretty good. So there's probably something I could do by storing to increase the speed of the algorithm. But the algorithm, we could talk about it a little bit, which is we are going through each of the edges. So if we have n edges, then yeah, we're going through each of the edges, and then we're multiplying by however long it takes to compute the find. And so I guess maybe the union find, that might be what's slow, because the slowest would be every time I need to go through, everything is able to be added, so I would have to go through, so it would be n squared essentially, because every single node I go up to all the parents. So I think there's some path compression that I can do, and then the space is the number of vertices. So yeah, if you guys learned something and have fun, please let me know in the comment section below, and also like this video and share with anyone you think will find useful. Also subscribe if you would like more content, and follow me on social media for more updates. Yeah, with that being said, I really hope you guys have fun and learn as much as I did. And yeah, I'll see you guys in the next one.